Range, sure. Let me think of a function that is sure. Let's look at a couple examples. Yeah. So I've got a couple different ideas about how to do this. Let's write a few things down here. Today is April 10th. Range. So when it comes to finding the range, I would say that there's kind of two wholly distinct methods for finding the range. One method is just graphically. So for example, if my function was something like, I don't know, the square root of x minus 2 plus 3, finding the range a different way is kind of challenging. We'll talk about it in a minute, but we can try to find the range here by graphing this. So first I'll point out, might as well get some extra practice in here as well. We're going to graph this by translating the original parent graph of just the square root of x. So here's our square root of x graph. Looks pretty typical. Oh man, I have to remember to bring a screwdriver with me next time because this is definitely in the way. Let me see if I can make this less in the way here. 1 second. Sorry. Also, as usual, if I get off camera, please let me know. I don't try to, but sometimes it's unavoidable. So here's the nice xy axis square root function. When I'm graphing it, I'm usually thinking about plotting the points 0, 0, 1, 1, and 4, 2. Here's my usual square root function. And then there's two translations happening here, or shifts, if you prefer that word. This square root of x minus 2, it always feels backwards when you're doing the horizontal thing, meaning, although we're subtracting 2 from x, that means we're going to end up moving 2 to the right. Here's how I think about it. In this first graph, x has to be 1 to get a value of 1. Here, x has to be 2 larger. X has to be 3, so that 3 minus 2 is 1 and the square root of 1 is 1. That's why it's pushing us 2 to the right, not 2 to the left, because the x has to get bigger in response to subtracting 2 from x. So this new graph that's shifted 2 to the right has an x-intercept of 2, and then we have the point 3, comma 1, and something else, comma 2. I really care mostly about the starting point here, 2, comma 0, or here, 0, comma 0. Finally, this plus 3 is happening outside of the function. So we're going to add 3 and we're going to shift up by 3 because all the y values are going to increase by 3. So if I look at f of x equal to the square root of x minus 2 plus 3, here if x was 2, I got 2 minus 2, which is 0, and the square root of 0 is 0. Here if x is 2, I get 2 minus 2, which is 0, the square root of 0 is 0, and 0 plus 3 is 3. So we're going to get essentially the same graph, just everything moved up 3 units. So I'm going to get the point 2, comma 3, and the point 3, comma 4, and it's going to have the typical square root shape. I'm going to label this point specifically because it's kind of important. It's where the graph starts. And we might as well talk about the domain and the range here. So I point out that the domain, well, just looking at the graph, I can see that the x values start at 2, and then they go further right. So my domain is 2 inclusive to infinity. You also could have found that in the usual way by saying, oh yeah, I've got a square root, and we know the stuff inside the square root has to be greater than or equal to 0, which means that, excuse me, x has to be greater than or equal to 2, or our domain is everything from 2 inclusive to infinity. In a similar way, graphically, the range being all the y values, well, our lowest y value is a y value of 3, and we do get that y value. So we're starting at the low of 3 included, and then going up, 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 and away. And I would say that for this function, there's not really a better way to do it. Because finding its inverse and finding the domain of its inverse is less good. There's not a good way to say it's less good. It's just less good. I can't really, I'll try to think about why in a minute here, but let's talk about a totally different kind of example now. Maybe not totally, but somewhat different. Let's say we want to look at now g of x equal to, I'm a fan of this kind of function, 2 plus 5x over x minus 4. If we really tried, we could probably graph this, but not that we shouldn't want to graph things. Graphing is a very, very useful way of representing a function, but it's not always easy to do. And if we're trying to find the range, unless we're already given the graph or can access it easily, there is another method that doesn't require anything. Well, it doesn't require any graphing, I should say. So to find the range of g of x, we're instead going to find the domain of the inverse function. That's the other way we typically talk about finding the range. So to do that, we have to find the inverse function first. Now, this does depend on the function being invertible. This original function is invertible, although showing that's probably not what we need to spend our time doing. So to invert this function, we're going to start with first writing y equal to 2 plus 5x over x minus 4. Interchanging the x's and y's. So then we get x equal to 2 plus 5y divided by y minus 4. And then solving for y. So always my first step is to multiply both sides by that denominator. So I'm going to get x times y minus 4 equal to 2 plus 5y divided by y minus 4 times y minus 4. And the y minus 4 divided by y minus 4 divides to 1. On the left-hand side, we distribute the x. So we get x times y minus 4 times x. On the right-hand side, we have just 2 plus 5y. And then we want to collect all our y terms on one side and all the other terms on the other side. Because if we're trying to solve for y, we have to isolate the y's. So subtract 5y to the left and add 4x to the right. So now I have xy minus 5y on the left equal to 4x plus 2 on the right. The whole reason we did that was so that then we can factor a y out from all the terms on that side. So we're going to have y times x minus 5 equal to 4x plus 2. And then dividing both sides by x minus 5, we're going to get y equal to 4x plus 2 over x minus 5. Or if you prefer, you could write it as g inverse of x equal to 4x plus 2 over x minus 5. And then we can answer the question, what's the domain of g inverse? Well, we want everything except for where the denominator is equal to 0. So we want to make sure we exclude x minus 5 equal to 0. In other words, x equal to 5. So we want everything except for 5. So here, the domain of g inverse, which is the same as the range of the original function g of x, is going to be every real number exclusive of 5. Before I forget, I'm going to pass around the attendance form. I'll see you right there. Thanks. No, I don't want to say that. So 2 different ways to find the range. You can find it graphically if you have the graph, or you can draw the graph, or you can find it by finding the domain of the inverse. Question, I like that. I have lots of things I can talk about too, but are there other questions about anything really? About anything math related? Yeah.
Can we do the same style, but graphing like a natural log versus like sine graph or something like that? Like cosine.
Sure. So as far as like finding the range?
Okay, I guess not similar. Just like how to graph like a natural log when just given the function.
Okay.
And then using transformation.
Sure. So let's start off with just the very basics about logarithms. So graphing logarithms. So I would say the logarithm. Oh, so speaking of this, we'll say this in a minute, actually. So let's say we were going to start off with the very generic f of x equal to the natural log of x. Yes, we will transform in a minute, but I want to just show you what the original one looks like. So when you graph this function, it's going to have the following attributes. An intercept at 1, 0, a vertical asymptote at the x-axis, and then it gets bigger and bigger and bigger, albeit very, very slowly. So notably, some things to be aware of. The domain here is everything that's positive. Yeah, we'll talk about that in a minute as well. The range here is all real numbers. You get everything from negative infinity all the way up to infinity, even though, again, it goes very, very slow. You get an x-intercept of 1, 0. You get a y-intercept. No, you get no y-intercept. And you get a vertical asymptote at x equal to 0, and you get no horizontal asymptote. I think I mentioned this before, but I'll say it again. These things are exactly the inverses of the exponential function e to the x. So if we were to, might as well put this graph on here as well. Let me label things here. Here's my f of x equal to the natural log of x. And then in red, here is our exponential function, g of x equal to e to the x. I'm not going to write them all down because we've written them all down before, but I will just point out this function has all of the inverse things. It has a domain of all real numbers. It has a range of all positive numbers. It has a y-intercept of 0, 1. It has no x-intercept. It has a horizontal asymptote of y equal to 0. And it doesn't have a vertical asymptote. So everything for these two inverse functions, all the x and y things interchange. But I think your question was more about how to say take a function like this and graph its graph like a transformation of it. One more thing I'll say for one moment, and again, my being not quite as young as you all, my hand's not the best with this, but everybody look at your right hand. Yes, put down your pencil, look at your right hand for a second. On your right hand, there's a pretty good approximation of an e to the x function right there and a natural log of x function right there. It's pretty useful, I think. So on your right hand, e to the x and natural log of x. On your left hand, e to the negative x and natural log of negative x. Not quite as useful, but okay. But yes, remember that your right hand has the natural log function and the e to the x function. It's pretty great. You can thank Grant for that one. He's the one who taught me that many years ago. So there's one more thing that was on my mind about this, though. Where'd you go? Oh, I know what it was. Oh gosh. Oh yeah. So I just want to point out one more thing before we actually get to your question is, why can't we find or take the, say, log base 2 of 0? Why can't we take the log of 0 or a negative number? Well, so here's why. I will point out y equal to log base 2 of x is equivalent to, well, the base is 2, the power is y, and the argument is x. So if we were going to take log base 2 of 0, it would have to mean that there was some, sorry, that's a 0 there, that there was some y value so that 2 raised to the y power is equal to 0. But that's not true, right? 2 to the y, for any input, 2 to the y is always bigger than 0. So this has no solution, which means that this log base 2 of 0 is undefined. And the same is true if we were trying to take the log of a negative number, right? For the same sort of reason, log base 3 of -9 doesn't exist. Because if you try to set log base 3 of -9 equal to some x, and then rewrite this as the base 3 raised to the power of x equal to -9, there's no solution there. Or as I like to say, if you have a positive base to any power is always positive. So let me write that down. B to the X is always positive as long as B is positive itself. Always true. And we don't really deal with negative bases. And you might say, James, I think you're a liar because I have seen something like y equal to negative 4 to the x. And I say, well, that still actually is a positive base. You have 4 to the x first, and then after you find what 4 to the x is, then you take the negative of that. So this still is a positive base. If someone wrote it like this, which they never will, that would be a negative base, and that is problematic. We don't encounter that because it's just got too many issues to deal with. It's not well defined for a lot of those. If you try graphing this on Desmos, you get like a lot of dots and you'll be missing most of the graph. Okay, so I know it took me a while to get there, but finally coming back around to say graphing something like, I don't know, f of x equal to log base 4 of x plus 2 plus 3. So a few things to consider here. I'm taking my original log graph and I'm doing essentially two transformations. Yeah. I'm shifting it left by 2 and up by 3. So here's what I'm thinking about happening. My original logarithm graph, which has this general shape, I'm going to shift it left 2. So here's my y equals log base 4 of x. And then if I shift it left 2, look at y equals log base 4 of x plus 2. Well, this point that was at 1, 0 is now going to move 2 to the left. And 1 minus 2 is negative 1. So we're going to end up over here with that x-intercept. Also, probably even more importantly, my vertical asymptote has moved. My vertical asymptote was x equals 0, and I've shifted the entire graph 2 to the left. That means my vertical asymptote has also shifted 2 to the left. So here's my new vertical asymptote at x equal to negative 2. Another way to think about that, especially for logarithms, is that your vertical asymptote is essentially going to be the end of your domain. So if we were finding the domain for this function here, I said, okay, yeah, for the domain, we have to set the insides x plus 2 to be greater than 0, which means that x has to be greater than negative 2. So x equal to negative 2 is going to be where the vertical asymptote lives. Yeah.
So no matter what the base is of the log, it's always crossing at 1.
Before we've done any transformations, yes. Yep, no matter what the base. Yeah. I will point out it's less likely to occur, but for logarithms, you can also have bases less than 1. Like you have a base of 1/2 or a base of 1/3. It's pretty atypical, but if you did have those, it would flip the graph vertically. And so the logarithm would look like it was flipped over and be coming down like that instead of going up like that. But again, it's very atypical. So I wouldn't worry too much about that. Unless you see it, and then let me know. And then finally, I'm going to move everything up 3, which for a logarithmic graph doesn't really look like you're doing a whole lot. So shifting everything up by 3 to get my function f of x equal to log base 4 of x plus 2 plus 3. Everything moves up 3. So the vertical asymptote doesn't move, right? A vertical asymptote shifted up 3 is still a vertical line in the same spot. So my graph is going to look like, this is where I might have to actually plot some points to have a good idea of how things look, or at least maybe better word here is label some points. So the point negative 1, 0 is now going to be moved up 3 to negative 1, 3. And I had some y-intercept here, whatever it was, and we are going to find it, is going to move up by 3. So it's probably, I don't know, like here-ish. So here's what my graph kind of looks like. Oh, I have a new x-intercept as well. It still looks the same. I just moved everything up 3. If I were graphing this, and I am, I would probably want to include my intercepts if they were not too terrible. So how do we find the y-intercept? What's our starting place? Well, if we're on the y-axis, What's true about all the points on the y-axis? We haven't moved left or right. Right, we're just going up and down. So if I move left or right, you know that x has to be 0. Right? If we're on the y-axis, all those points are like 0, 1, 0, 2, 0, pi, 0, 7. X is always 0. So the way we find the y-intercept is by setting x equal to 0. So then if I set x equal to 0, my y value is going to be f of 0, which is log base 4 of 0 plus 2 plus 3. Oh, this one's always weird. Okay, what's log base 4 of 2? What is log base 4 of 2? So the question here, when I'm looking at log base 4 of 2, is 4 raised to what power is equal to 2? And here the answer, in my opinion, is unfortunate because it can be misleading. We know that the square root of 4 is equal to 2. In other words, 4 raised to the 1/2 power is equal to 2. So here, log base 4 of 2 is equal to 1/2. So our y-intercept is going to be 1/2 plus 3, which is 3.5. Yeah. The reason I say that's unfortunate is because it's also true that 4 multiplied by 1/2 is equal to 2. But that's not why the log base 4 of 2 is equal to 1/2. It's because 4 to the 1/2 power is equal to 2. Kind of weird, I know. So this point here is 0, 3.5. And then my x-intercept, I can find that as well. And just like we found the y-intercept by setting x equal to 0, we're going to find the x-intercept by setting y equal to 0. So to find the x-intercept, we're going to set y equal to 0, which means we're setting the entire function equal to 0. This one's going to be kind of weird. Not that weird. So we're going to set log base 4 of x plus 2 plus 3 equal to 0. And now we're going to solve this. So let's see here. I'm going to subtract 3 from both sides. Log base 4 of x plus 2 is equal to -3. And then I'm going to take this logarithmic equation and rewrite it as an exponential equation. What's my base? That's why we say log base 4, right? Not just log 4, we say log base 4. Oh yeah, the base is 4. What's the exponent? This part's always the hard part. Is the exponent the thing that we're taking the log of, or the thing the log is equal to? So the exponent's always the thing the log is equal to. I often will draw a little picture like this, where I go 4, and then I go 2 the -3 equals x plus 2. That's the way I'm really kind of imagining. That's the picture that lives in my head, is I go from there, and then I go over there, and then I go over there. So 4 to the -3rd power is equal to x plus 2. What's 4 to the positive third? 4 times 4 is 16, times another 4 is 64. So 4 to the -3rd is 1/64. So we have that x is equal to 1/64 minus 2. Or -2 plus 1/64, which seems reasonable based on where it's living on my graph. It's just a little tiny bit to the right of -2. So that seems very, very plausible. So that point there, I don't want to label it right there because it's kind of close. But that point there is x is -2 plus 1/64, and my y value is 0. So there's a not too terrible graph of a logarithmic function. It's kind of terrible. Let's look at one more thing with transformations because we didn't talk a whole lot about them. And I think it is probably something we should spend a little bit of time on. So let's look at one more example of this. Not this exactly, of transformations in general. So let's see, what terrible thing can I come up with? Let's do the following. Let's graph one period of, sure, f of x equal to, let's do that. 3 sine of 1/2 x plus, let's do minus. I keep doing pluses here. Minus the minus sign, you can tell, -2. So we've got a few things going on here. So I would say when I'm graphing a function with transformations, like I'm focused on the transformations, I almost always work from the inside out. Meaning I start at X and then I see what's being done to X. If something is being added or subtracted to X, it means I'm shifting left or right. If something's multiplying X, it means I'm stretching or squishing horizontally. Anything that happens to X before like the function happens affects the graph horizontally, either by shifting or stretching, or if there's a negative sign by reflecting horizontally. Whereas things that happen outside of the function, like the 3 here and the -2 there, affect the graph vertically. That 3 is going to either stretch or squash it vertically, and the -2 is either going to shift it up or down vertically. So let's see here. For trig functions specifically, we know that the usual period of, let's say, y equal to sine of x is 2 pi. We have to do one full revolution of the unit circle to go through all the angles to get one whole graph. So the 1/2 x there, what does that do for us? Well, let's see. If we look at, excuse me, I'm going to say more here. This is 2 pi because your angle has to go from 0 to 2 pi to get all the values we want, right? Let me even graph one period of sine here. Has the usual shape. Maybe it has the usual shape. That's okay, that's usual-ish. So there's one period of sine. It starts at the origin. At pi over 2, it has a value of 1. At pi, it's back to 0. At 3 pi over 2, it has a value of -1. And finally, at 2 pi, you've gotten back to where you started with the value of 0. So we're going to take that graph and we're going to do 3 transformations to it. And first off, this 1/2 x, well, if you look at sine of 1/2 x, to get the full period, now we need our angle 1/2 x to go all the way from 0 to 2 pi. And if we isolate x, and if we get x all by itself, if we multiply everything by 2, 2 times 0 is 0, 2 times 1/2 is 1, and 2 times 2 pi is 4 pi. That means our new period has doubled from 0 to 2 pi to 0 to 4 pi. And again, here's what I'm thinking about it, right? If I'm multiplying by 1/2 here, x has to be twice as large as it was to get the same values input into the sine function. So our new period is from 0 to 4 pi. I should say our new single period is from 0 to 4 pi. And then the 3 there. So I should say this is our period. The 3 on the outside there is going to stretch it vertically by a factor of 3. So we're going to have a vertical stretch by a factor of 3. When you stretch a sine function or cosine function by some factor, we call that the amplitude. So this is called the amplitude. And finally, the -2 out there will shift the graph downward by 2 units. If we're trying to draw out all the little intermediate graphs, here's how this is going to look. So here's our original y equal to sine of x. Doing the first transformation, we're just stretching it to be twice as long. Oh, there's another fun way of saying this. So one other way of looking at this 1/2 right here is saying that's how many periods you get from 0 to 2 pi. So from 0 to 2 pi, we're going to get half a period. From 0 to 4 pi, we're going to get one full period. So usual shape. Still goes as high as 1, as low as -1. And I meant to label it. This is y equal to sine of 1/2 x. So we go here, and then here, and then here. There. So again, same shape, it's just been stretched horizontally. And we could label these intermediate points. This is going to be 2 pi, pi, 3 pi. And then we're going to stretch it vertically by a factor of 3. And we're going to run out of room. Happens sometimes. So same graph, except now we're just going, in fact, you know what? Let me do this instead. Do I have enough room here? Maybe. Let's use a different color than this. So now what we're going to do this graph is we're just going to stretch it by a factor of 3. So we still get 0, 0, but now instead of getting pi comma 1, we get pi comma 3. And we get 2 pi 0, 3 pi comma negative 3. Oh, you're in the way there, sorry. And then finally back to here. So we're stretching it out. Still has the same general shape, just it's been stretched. Lastly, and I didn't give myself quite enough room, but we will make it work. Oh no, I did. I have enough room because we're shifting down. Good choice. Good choice. I'm excited when things work out nicely. So we're taking this whole graph and moving everything down 2 units. So when I shift specifically a trig function up or down, I like to draw what I call a new middle line. So if you haven't shifted up or down, the quote unquote middle line is the x-axis. So I'm just going to draw a new middle that is 2 units below that. Kind of like a horizontal asymptote, but it's not an asymptote. It's just a new middle. It helps my graph look decent. And then I know from that new middle that my graph is going to go as high as 1, 2, 3 units above that, and as low as 1, 2, 3 units below that. But then it's just going to be exactly the same graph, just shifted down 2. So I'm still breaking it up in half, and then each of those in half again. I start in the middle for sine, and then at the next important value, I go up to the top, which is 1, not on the x-axis, then back to the middle, then down to the bottom, and then back to the same y value we started with. And you try to make it look not too pointy. It takes practice. Cool. So transformations are useful, but we don't want to spend all of our time talking about them because there's lots of other things to talk about as well. What else is on your mind? You don't have to say anything. I've got plenty to say. I like to know if there are things that are really like, I really want to know about this. But, well, I will say you're welcome to interject at any moment, but let's talk a little bit about solving some trigonometric, some logarithmic and exponential equations. Let's see. Yeah. Good. So a couple of examples, and we've already kind of addressed this a little bit, but let's look at a little bit more. Let's say we want to solve the following. Here is our next one. See my paper over here? Yeah. Here's our first one. So I want to solve something like log base 2 of 2x plus 1 is equal to 3. I would like you all to write down the first step of what we should do next. Give you like 40 seconds. 45. So I see an x I'm trying to solve for, it's inside the logarithm. And if I'm trying to use something outside of the logarithm, I essentially have to rewrite it as an exponential equation. I should backtrack that a little bit. That's one way to get there, but it's the same as another way to get there. So I would think of just rewriting it as our base is 2, our power is 3, and it's equal to the stuff inside the log, which is 2x plus 1. I should point out another way to get to the same result is to instead think of writing both sides as powers of the base that we're already using. So you can instead think of this as 2 to the power of log base 2 of 2x plus 1 equal to 2 to the power of 3. And then the 2 raised to the power of log base 2 of some stuff, those two functions undo each other and you're just left with the 2x plus 1. So that exactly gets you to the same spot. 2x plus 1 equal to 2 to the third. It's fine to think of it either way. There's nothing more to say there, really. It's fine to think of it either way. Do think of it whichever way makes more sense to you. And then solving this is not too terrible. We've got 8 equal to 2x plus 1, subtract 1. We've got 7 equal to 2x, divide both sides by 2. 7 over 2 is equal to x. Or if you prefer, 3.5. Something that is true about some logarithmic equations is you have to make sure your answer is still in the domain of the original expression. Here, this totally is. If you plug in 7/2 for x, 2 times 7/2 is 7, plus 1 is 8, and it's definitely allowable to take the log of 8, whatever your base is. Let's look at another one here. Sorry, I keep losing track of my papers here. Yeah, let's think about that for 1 second. Sure. Okay, let's say we have the following. We have, sorry, I want to make sure this comes out somewhat decent here. Sure. Log base 3 of x to the 5th. That's sure, that's fine. Minus 3 log base 3 of x is equal to, let me think for a second here. Sorry, I'm trying to make this work nicely. Oh my gosh, sorry. Sure, let's go that way. We'll hope that didn't do something dumb, but it'll still work out. Okay, so we're trying to solve this equation. And unlike the previous equation, you've got multiple logarithms with x's in them. So before we can really do anything, we have to be able to combine those logarithms together into one logarithm. And before we can really do that, we need all the logarithms to have the same coefficient, usually either of 1 or -1, meaning we don't want this 3 here. We would much rather have that 3 as the exponent of the x there. So we're going to rewrite this as log base 3 of x to the 5th minus log base 3 of x cubed, bringing that 3 up as the exponent of x. Still equal to 4. And then we're going to combine these logarithms using the quotient rule for logs, which says if you have a logarithm minus another logarithm and the base is the same, you can divide the arguments. So we can rewrite this as log base 3 of x to the 5th divided by x to the 3rd is equal to 4. We can simplify the insides. That's going to be log base 3 of x squared. Ooh, that's an interesting idea that I hadn't noticed before. And at this stage, you could rewrite the equation. You could say, hey, I'm going to write this as 3 to the 4th power equals x squared. But I just noticed something that could make it even a little easier. We could actually bring that 2 back down in front. We could say, hey, I've got 2 times log base 3 of x equal to 4, and then divide both sides by 2 to get that log base 3 of x is equal to 4 divided by 2, which is 2. Which then tells me that I get 3 squared equal to x. And that seems easier. Additionally, it avoids the complication of having a possibly illegitimate answer. So here, I will point out that x equal to 9 is totally safe in our original expression, right? You've got 9 to the 5th is positive and 9 is positive. We're safe, right? We don't have any illegal answers here. But if we had done it this way instead, which is totally fine to have done it this way, what's 3 to the 4th power? It's always a tricky one, right? Because you're like 3 times 3 is 9, times 3 is 27, times 3 is, it's easier to do 3 times 3 is 9, and 3 times 3 is 9, and 9 times 9 is 81. So then you're trying to solve 81 equal to x squared. If you think about all the solutions are x equal to positive 9 or negative 9. But then in this expression, negative 9 is not allowed to be an answer because you can't take the log base 3 of negative 9. It's totally fine to plug in negative 9 here because negative 9 squared is positive 81. But you have to look back at the original expression and say, oh, negative 9 is not allowed. So just be careful when solving logarithmic equations. Sometimes you encounter what we call extraneous answers or extraneous solutions that are a solution to some part of the equation, but not a solution to the original equation. Kind of what time things out. Okay. So let's look at a couple more things here and then long. Solve the following. I keep looking at the wrong place. Sorry. What happened to me? Change rooms on there. Where'd you go? Oh, I did like that too. All right. So let's say we want to solve the following. I want to solve 10 to the power of 2x plus 7 is equal to 4. So here's what I would say. Whenever you have a variable in an exponent, or something that anything you want to get out of an exponent because you're trying to isolate it, that almost always involves the use of a logarithm. And you can use really any logarithm you like. What I mean by that is any base you like. You can use log base 2, log base 3, log base 7, log base 10, log base e. But I will tell you the standard choices are log base 10 or log base e. And usually either one of those is perfectly good, but if you have one of those two numbers already showing up as a base, it is almost always preferable to use that base. So even though you could solve this using the natural log, log base e, we're going to use the log base 10 because we have 10 to a power. So I'm going to either take the log base 10 of both sides. And again, I'll remind you that when you write log without a base, that's the abbreviation for log base 10. Or if you prefer, you could imagine rewriting it as a logarithmic equation. What is my base in this expression here? It's a good question. I feel like I haven't asked that very well. So when I'm saying what is my base, what I really mean is what's the thing that's being raised to a power?
Shouldn't it be log based 4?
So we could use log base 4, but we're going to use any base we want.
Like the log base 10, shouldn't that be 4 in the parentheses?
That should be. Thank you very much. Yes. Good. Yes. Definitely. That's a 4. Can't you tell? Yeah. Good call. Right. Because I took the log on both sides, and there was a 4 on the right side, not a 10 on the right side. So as I will say, if you see a mistake, don't hesitate to let me know. I don't do it on purpose. Just let me know. So here we could say, oh, we have log base 10, which I am going to write this time, of something should equal the exponent. Well, the exponent is 2x plus 7, and the something has to be the 4. Right? If we rewrote this as an exponential, it would be this raised to that power equals that. So what I'm trying to point out is just you can undo an exponential thing by thinking of it either way. You can either rewrite it as a logarithm, or you can take a log of both sides. And either way, it's going to achieve the same result because here, this 2x plus 7 as a power, powers get to come down in front. So you've got 2x plus 7 times log base 10 of 10 equal to log base 10 of 4. But log base 10 of 10 is equal to 1. Because 10 to the first power is equal to 10. So really, either way we slice it, we have the exact same equation. 2x plus 7 equals log base 10 to 4, or 2x plus 7 equals log base 10 to 4. And then solving it the rest of the way is just a couple algebra steps here. We're going to subtract 7 from both sides and get 2x equal to log of 4 minus 7. And then finally divide both sides by 2 and get x equal to log of 4 minus 7 divided by 2. And that's as good as it gets. That's our exact answer. To get an approximation of that answer, we would need to use a calculator. I will also say, for problems like this, teachers have a typical maybe predisposition towards using the natural log, the log base, just because it's the one that's easiest to write and comes up very often. So even though it makes more sense to use log base 10 here, you might see someone solve this by taking the natural log of both sides. Let me just show you what that looks like, because I think it is worthwhile. So here we use log base 10. Here we're going to use the natural log. So we take the natural log of both sides. Why am I even doing that? How does that help me? What does it allow me to do? It allows me to bring this exponent down in front. That's why we take a natural log or any log of both sides of the equation, is usually to get that exponent down in front of the logarithm. So here we're going to have 2x plus 7 times the natural log of 10 equal to the natural log of 4. And then you have a couple choices about how you do this. I would probably, I don't know. I'd probably distribute first and say I have 2x times natural log of 10 plus 7 times natural log of 10 equal to natural log of 4. And then subtract 7 natural log of 10 from both sides. And say I have 2x natural log of 10 equal to the natural log of 4 minus 7 times the natural log of 10. And then finally, divide both sides by 2 natural log of 10 to get x equal to the natural log of 4 minus 7 times the natural log of 10 divided by 2 times the natural log of 10. Same answer, just looks different. Either way is totally legitimate and acceptable and is not seen as like they did this some weird way. No, this is a totally normal way of doing this. All right. Not enough of that? Maybe. Why don't you all try one? Let me give you one to try here. I would like you all to solve the following equation. E to the 5x plus 1 is equal to 6. What logarithm should you use here? The natural log, because the natural log of b is 1. So go ahead and try that. Start by taking the natural log of both sides. Then I think talk about some of that. Bless you. All right, you guys are looking like most of the way through it. So the first step here would be to take the natural log of both sides. At least that's usually that's how I usually think, right? You could also think of rewriting it as the log base e of 6 equals the exponent. But I think it's easier to say to yourself, I'm just taking the natural log of both sides. So then on this side, you could either bring down the 5x plus 1 until you have 5x plus 1 times the natural log of e equal to the natural log of 6. And then the natural log of e is just 1. Or if you prefer, you could have said to yourself, well, hey, I know the natural log of e to some stuff. Those two things undo each other, and we just end up with the stuff, which is 5x plus 1, which is exactly what we've got. Either way is totally fine. So then solving this, 5x is equal to the natural log of 6 minus 1, and then x is equal to the natural log of 6 minus 1, all divided by 5. And sadly, this doesn't simplify any further, right? You can't combine the 6 and the 1 in any useful way. We're just kind of stuck. That's what we've got. All right. Yeah, okay. Oh, I have one more. Yes, let's do one more thing, and then yeah, we've got plenty of. I keep saying I have plenty of time in my head, and then eventually I don't. Not enough time. Let's look at one other thing that I noticed on one of the homework assignments that I thought was worth kind of looking at.
I think you could sign.
Yes, I definitely can. Let's say we have the following situation. The graph of f of x equal to c e to the k times t, where c and k are just constants. I'm sorry, I said f of x and I wrote a t. That's terrible. I should say f of t. Apologies. The graph of f of t equal to c e to the kt, where c and k are constants, passes through the following 2 points. What have I got here? I've got -2, 1 and +1, 9. Find c and k. I will point out that the way this is written, the first coordinate is my t value, and the second coordinate is my f of t value. What we're going to do is we're going to plug those into the function and see if we can solve for c and k. So let's use the first point first. So I'm going to plug in -2 for t and 1 for f of t. And I'm going to get, so using this point, we're going to get 1 for f of t equal to c e to the k times -2, or -2 times k. Unfortunately, I can't really solve for c, or I mean, I can isolate c here, but I'm not going to be able to find a value for it yet, because if I isolate c, it'll be in terms of the other constant k. So instead of doing that, let's move on to the second point and see if we can get anything from that. If we plug in the point 1, 9, we're going to get 9 equal to c e to the 1 times k. Okay, well, none of these are easy on their own, but together we have a system of 2 equations and 2 unknowns. And if you have as many unknowns as equations, we should be able to solve that system. So what I would probably do here is isolate c in both of these. So here I'm going to multiply both sides by e to the +2k. I'm going to say that c, actually I'm going to rewrite it as c divided by e to the +2k equal to 1, and then multiply both sides by e to the 2k. So e to the 2k is equal to c. Similar deal over here, I'm going to divide both sides by e to the k. We get 9 divided by e to the k is equal to c. And then I can set each of these things that are equal to c equal to each other. Right? If they're both equal to c, they both have to be equal to each other as well. So then we're going to say that e to the 2k is equal to 9 divided by e to the k. We're going to multiply both sides by e to the k. On the right-hand side, we get just 9. On the left-hand side, e to the k times e to the 2k. What do we do with those powers? We add them. And k plus 2k, well, 1k plus 2k is 3k. So we get e to the 3k equal to 9. Then we take the natural log of both sides. So natural log of e to the 3k equals natural log of 9. But the natural log of e to the 3k is just 3k. And finally, dividing both sides by 3, we get k equal to the natural log of 9 divided by 3. Or if you prefer, 1/3 times the natural log of 9. I wouldn't do anything else here, but I would point out if for some reason that was a 1/2 instead of a 1/3, I would take the extra step of simplifying it by bringing that 1/2 up as the power, because 9 to the 1/2 power is the same as the square root of 9, which would simplify nicely. So if you see a coefficient out there that you can bring up as the power of the argument and make things look nicer, it's usually worth it to do so. We're not quite done though, because we were told to find C and K, and we've only found K so far. K is 1/3 natural log of 9. Luckily, we have C equal to two different things that have K in them. So we could pick either one of these to plug K into to figure out what C is. I'll pick this one. So here we're going to get C is equal to E to the 2 times K, which is 1/3 times natural log of 9. I would probably normally do it like that, but I want to show you something that's going to happen more often than not. So when you have E to a power and you have a natural log in that power, it's usually a good idea to do the following. And a good idea is probably an oversell, but you can see something. So 2 times 1/3 is 2/3. You have 2/3 natural log of 9. And then just like before, when we had like the natural log of something to a power and we brought down the power, we can also go the other direction and bring that coefficient of the natural log up as the power. So this 2/3 we can think of as the power of 9. So what we really have here is E to the natural log of 9 to the 2/3 power. And then the E and the natural log undo each other, and we just get 9 to the 2/3, which unfortunately does not get any nicer. I mean, you can make it like the cube root of 81 if you wanted to, but that's not really any better than 9 to the 2/3 power. So I would probably just leave it like that. So that's my C value. Whoops. 9. It gets really, when I put my hand here, like it really makes it so much darker for me over here. I'm like, wow, what did the sun just get covered by a cloud? No, it's just my arm. So that's how we attempt a problem like that. Sometimes these are kind of gnarly if, well, in like in this example, where you are not given one of the points where 0 is your first coordinate. So if we had been given instead like 0, 3 and 1, 9, it would have been much easier to find the C value right off the bat and then find the K value after that. But if you're not having either of those with a 0 input, then it's much more. Okay. Let's spend some time talking about this log, semi-log stuff some more, because I do think I've definitely seen all your homework assignments and all of them have some of these log, semi-log questions. So we'll do one more hand one, and then the rest of it we'll talk about how we do like the stuff using either Excel or Google Sheets, or you can even do it using Desmos if you really like. But I think the Google Sheets way probably shows us the most, and it's accessible to everybody, whereas Excel you have to like have. So we should use Google Sheets because everyone can access it. But let's look at this problem first. And this problem is not exactly the same as, but is based on number 67 from section 1.5. I'm going to try not to write out all the words here because there's a lot of words. So let me see. So in a case study of the biodiversity of trees in the tropical rainforest, the number of trees, which we will call S, we came up with that letter, I don't know, was plotted against the area, capital A, on a log plot, meaning our data is the log of the inputs and the log of the outputs, not the actual values themselves. Get. And what we got was this resulted in a straight line, which is almost always going to be the case with these kind of problems, with a slope of 0.84 and a vertical axis intercept of negative 0.06. Find the equation that relates, that relates S to A. I left out, it's not really that important, but the reason that you chose the letter S, it wasn't the number of trees, it was the number of tree species, which makes a lot more sense in the context of the problem. So that's what we're talking about, the number of tree species as a function of how much area we are looking at. So here's what we're saying. And again, this picture isn't super necessary, but I like drawing. So on our horizontal axis, we have the log of A. And in the vertical axis, we have the log of S. How do I know which one goes on which axis? Because of the order they set things in here. Find the equation that relates the species abundance to the area. So we're thinking of the species abundance as a function of area, not area as a function of species abundance. It should usually be relatively reasonable to think about like what your input is and what your output should be based on like what kinds of things you're measuring, but not always. So just be thoughtful. And this is going to look kind of like this, where my slope is 0.84 and my y-intercept there is negative 0.06. Pretty simple line. We'll say that we have our capital Y equal to m times our capital X plus U plus B. So I'm using capital Y and capital X in the place of log of whatever. Whereas if I was using my actual variables, if this was semi-log instead, I would use capital Y and regular X. Capital Y is the stand-in for log of S, the vertical axis logarithm. Capital X is the stand-in for log of A. My B value here is negative 0.06. The rest of this process is just manipulating this thing using rules of logarithms to get back to S being all by itself. What's our base here? Well, what log base am I using? 10. Always 10 for these logs. Always log base 10. We're writing log because right. So I'm going to think of raising both sides as powers of 10. I'm going to write this as 10 to the log base 10 of S equal to 10 to the 0.84 times log of A minus 0.06, all as my exponent there. That's terrible. Okay, we're going to do a couple things. The whole reason we wrote this equation as exponents of the base 10 is so that 10 to the log base 10 of S gets to become just S. That's the whole reason why. So we're trying to write S as a function of A. On the right-hand side, there's some steps we always take. First of all, we have 10 to the something minus something. Or I would probably rather think of this actually as this plus negative 0.06. So I can rewrite this as 10 to the 0.84 times log of A times 10 to the negative 0.06. Because if you were to multiply these back together, what would you do with the powers? You would add them. There's two more steps we take because often in web work, they'll give you a question like this and say, like, write your final answer without using any logarithms. I've got a logarithm still in my answer, so I have to fix that. So I'm going to do this. I'm going to write this as S equal to, I'm going to write this part first because that's just typical. I'm going to write this part as, well, I'm going to bring that 0.84 up as the power of A. So I'm going to write this as 10 to the log of A to the 0.84. And then finally, 10 to the log base 10 of something is just the something. So we get S equal to 10 to the negative 0.06 times A to the 0.84. So we see that if we start off with a log-log relationship that is linear, we end up with a functional relationship. Is it an exponential function or is it a power function? Definitely a power function because your variable is being raised to a power. instead of your base being raised to a variable exponent. Okay. So let's go ahead and look at, well, actually, let's pause. Are there questions about this before we do something related, but a little more complicated? Yeah.
We can just leave it in that final form.
You might get a decimal approximation for 10 to the negative 0.06, but I would leave it like this. Yeah, 10 to whatever that power is times a to whatever that is. There's really no better. Again, you could simplify this further by, again, getting a not exact decimal approximation using a calculator. So in fact, if we did that, if we got what, 10 to the negative 0.06, about 0.870, right? So where do we stop? I don't know. So you could also think of this as approximately 0.87. But I would warn you, as far as web work is concerned, really does not like decimal approximations. So if you have to approximate something, wait until the last moment possible. All right, let's go ahead and look at another example here. So I think I have the frame here. One moment, please. Yeah, cool. Pick up that. Not the right one. Nope, that one is. Yeah, cool. Oh my gosh. Now I have to navigate here. It's going to be real fun. Let's see if I can grab this one here. Yes. So here is a question similar to ones on your web work where, yeah. You see that? Yes, great. So they're giving us a table based on the relationship between X and Y. And they're telling you that the relationship either is exponential or power. Meaning, if it's exponential, it's going to be linear on a semi-log. If it's a power function, it's going to be linear on a log. And our job is to figure out which one it is. So here's how we do it, or here's how I would recommend doing it. Sorry. So we're going to take this data, copy it, and then paste it. Oh my gosh, did you want to go away there? And that's not the right one. That's not the right one either. Let's sheet one over here, sorry. And paste it into two columns, which I have conveniently labeled X and Y. I would warn you if you're using Google Sheets, I don't know why this happens, but if you put the columns right next to each other, bad things happen. So make sure you give yourself a column between each of your pairs of columns. Because in addition to a column for X and Y, I also want a column for X. So I'm just going to do the easy things here and say this is equal to B2. And then I'm going to click there, grab that corner, drag it down. So it copies all those values. And then here, I want it to equal the log of those Y values. So I'm going to write equals log of C2. And then it wants to already pull it down for me. Great. That's exactly what I wanted. That's just giving me, right? If you look at these other entries, that's log of C3, that's log of C4, et cetera, et cetera. So I do the same. Whoops. Don't do that. Sorry, I'm clicking all kinds of places. And then same deal here. We want the log of the X's. So it's going to be log of, let's see, B2. And then for some reason, it doesn't want to drag it down there. Fine. And then here, I can just say that's equal to log of C2 again. And then drag them down. Cool. Great. We have all our data. Stop moving. Now we're going to try to see which of those gives us a better linear fit. So we're going to grab all of this, including the top row, so that we get nice names when we graph it. And then I have to remember where to find this thing. Sorry, let's move over here. So you go to, I believe it's insert. And then you go chart, I think. It's been a minute. And it gives you a nice chart. And then you want to know, well, how good is this? So here's what you do. You click on the little dots here. Nope, you don't click on it. Sorry, it's always the process to remember, like, why does that feel like it's that's better? So you go over here and customize. You go down to series. And you do a couple things. You want to include the trend line. And then you want to show R squared. R squared is a measure of how good your fit is. The closer to 1, the better the fit. The closer to 0, the worse the fit. So it's a pretty good fit, right? R squared is 0.975. That's pretty close to 1. And then if it were the one you would want, you would also then click on the label to use equation, and it gives you the equation. Log of y equal to your mx plus b. Awesome. But that might not be the right one. We need to check the other one to see if it's a better fit. So we'll move this one somewhere out of the way. Sure, you're out of the way. Fine. And then we'll do the same thing for these two guys. So again, highlight them fully. And then we're going to insert a chart. Oh, it looks straighter. It's probably the winner. And then, we do the same thing with this chart. We go over to the customize. We go to the series. We turn on the trend line. We turn on the R squared. Oh, R squared is 1. Well, that's obviously the winner. And then we also get the equation. So there's your equation. Now, I'll point out one thing here. I don't know why it does this, but for some reason, it doesn't want to give you the name. Like here, it's got the name log y versus log x. But here in my equation, it doesn't give me log x. It gives me just x. So make sure, since this is what we're using, we have to write our equation is log of y equal to negative 2.3 times log of x plus 1.05. So that's what we're going to do. So maybe, probably. Sorry, it's should have been much easier in the other room. Oh well. Sometimes you get what you wish for. So after all that, and I know you can't see what I'm writing just yet. Let me turn that back on. There we go. Move. So after all that, I forgot what I said it was. So we had the log of y equal to, I think it was, but let's double check. It was log of y equal to negative 2.3 times log of x plus 1.05. So that would be our functional relationship before we solve for y. I'll point out this is clearly going to be a log-log relationship, meaning we are looking for a power function. I should be more explicit. It's a linear log-log relationship, meaning we're looking for a power function. So then we do the same things we just did for the previous problem. We're going to solve for y. Interesting. I didn't think about that. That's cool. So by rewriting this as 10 to the log of y equal to 10 to the negative 2.3 log of x. I'm going to skip a step here and write 10 to the 1.05. Right? I know that I have 10 to something plus something. It's the same as 10 to the first thing times 10 to the second thing. It's totally okay to skip that step. On the left-hand side, we get y. On the right-hand side, I'm going to do two things. I'm going to do one thing. I'm going to rewrite this with the negative 2.3 as the power. So that's going to be 10 to the log of x to the negative 2.3 times 10 to the 1.05. And finally, our last step, we're going to rewrite this as y. So I like to write the constant first, not for any good reason other than it just is ingrained. 10 to the 1.05 times 10 to the log of x to the negative 2.3 is x to the negative 2.3. And what's kind of neat, I think, is if you actually plotted the original data and then graphed this curve, it should go through those data points. In fact, I think we can do that on Desmos real quick here. Let me see. Sorry, I will show you that in a second. So let's see. Can I plot? Can I? Yeah, cool. It'll totally just paste it right there. That's nice. And then there's my data points. And then if we graph the function we just came up with, which was y equal to 10 to the power of 1.05 times x to the power of negative 2.3. Why'd you go over there? Probably because I hit a button accidentally. Look at that. A perfect fit. Kind of great. So those sorts of questions where they're giving you a table of data and asking you to determine if the relationship is exponential or power function and what it is, this is the process for doing that. You throw that data into Google Sheets or whatever way you prefer to do it, although I think it's really relatively easy to do it using Google Sheets. And then you go make a chart. You turn on all the things, which you find in the, I always forget where it is. Where did I find that? I found it in the, I think the customize part. Right? Yeah, you go over here, customize, specifically customize, you go down to the part called series, and that's where you find all the things. You find the trend line, you find the R squared, and you change the label to use equation. And that'll give you everything you need to then answer the question. There's a video of me doing this for a couple other examples already on Canvas. Are there questions about this? It's a bit much, but it is very doable once you've done it once or twice. So don't be afraid to try this. It's not that bad. I think it's kind of fun after you get comfortable with it. Fun might be an oversell, but it's not the worst thing you'll ever see.